All right, folks, today we have seen how to do some predictions for future solar energy production using our equation that we've generated. And this is sort of the generic form here. I don't have our specific number values in. You calculated those recently. So I've just put the generic, m for slope and b for y-intercept here. You've got specific numbers now, and we got this nice equation. Really what we're doing is figuring out how to incorporate weather into the situation. And you've got some data now to facilitate that, but how do we use that data to actually make some sense out of the situation? Well, let's think about what's going on. We've got our solar panels that are hanging out on the roof of a house. And I'll draw out my little roof like this. That's obviously a house. It's got a door and everything. It's got some solar panels on it, and we've got some amount of sunlight coming at us from the sun. And so far, we have a pretty good prediction equation if we have a nice and sunny day. But we know that in reality, you've got clouds that sometimes obstruct some of this sunlight here. I'll draw some little clouds in the way that are going to cause some issues. So the question is, how do we take those into account? Well, probably the easiest way to think about this is that weather phenomena, clouds and things, are going to reduce your solar intensity. In the past, we have calculated solar intensity using things like our solar angles, which we know how to calculate. But this works really only if we have no clouds obscuring the sunlight that's coming in. So we can get some number that would exist if it were completely clear. But then also what we've picked up from our weather data is we actually have some data that estimates what percentage of sunlight actually makes it to the ground. So what we're essentially going to be doing here is we're going to use the same prediction equation, because this equation seems to work pretty well. We're just going to modify the solar intensity that we put in here by taking into account the fact that, not all of my sunlight actually makes it through my clouds. So we have essentially solar intensity if sunny, and we're going to multiply that by what we're getting from our weather data, which is essentially percent sun. And this is going to give us, we can call it actual sun, or we could call it corrected for weather. Now, of course, doing this depends on having good data for our percent sun, and we'll rely on the data that you've seen that I've shared with you in that weather data set. Something we could also use, and if we had to deal with this stuff into the future, projecting it into the future, we have data on averages, historical averages. For the month of November, for instance, we know that the percent sun on average is 50%, so half of what it would actually be. So we could, on average, say, on any given day, you'd get half of the actual sunlight or that you would have gotten if it was totally sunny. So this is how we'll deal with it. We're going to use this exact same equation that you've been using. The only thing we're going to change is we're going to change how much the solar intensity is by using actual solar intensity instead of what we've been doing in the past. So what we'll actually be doing is we'll be calculating corrected prediction for energy that's corrected for the weather. We'll use that same slope value that you found and calculated recently. And instead, we'll be using this in for that, for our corrected intensity. And we'll still be using that same y-intercept value. So it's the same equation. We're just using the weather information to change what we think of when we think of how much sunlight is actually hitting our panels. Seems somewhat straightforward, and this is indeed a pretty simple way of dealing with it. What you're going to be doing, of course, is seeing and investigating how well this strategy actually works for us in terms of making predictions. That'll be the task you're about to work on.